Hi, I'm Todd Austin from University of Michigan. Today I'm going to be going through part 7 of my hardware security video tutorial. This is a new part to the originally 6-part series. And in this 7th part, we'll be looking at recent hardware security attacks. Things that have happened in the 2021 to 2024 timeframe. So if you're looking to get up to date on the most recent, most innovative hardware security attacks, this is a great video to watch. Let's get started. Before I jump into the material, I want to talk a little bit about the previous portion of this tutorial. In the first 6 parts, we talked about why hardware security is important, what are the security basics you need to know to be a hardware security person, how does hacking work both software and hardware hacking. Then we learned about side channels, which is the other side of the hacking coin. And then we looked at security defenses, both software and hardware security defenses, and why they don't often completely stop particular vulnerabilities. And then we looked in the last part, part 6, at emerging defenses and really strong security technologies that actually move into the privacy technology arena. So if you're interested in learning more about hardware security, definitely check out the first 6 episodes of this tutorial series. So today I want to talk about new attacks, very recent, within the last typically 3 years or newer attacks. And I've divided them, there's 14 attacks that I'm going to go over today, and I've divided them into 3 bins. The first are Spectre-based attacks because, Spectre is just the gift that keeps on giving, and there's so many new and interesting, really innovative variants of Spectre. I want to talk about some of those today. And then I'm going to talk about some new and novel, interesting side channels, things that kind of break out of the branch predictor and the cache side channel and start to look at some really interesting things like, power gating side channels, DRAM side channels, etc. So it's really interesting material from a side channel point of view. And then finally, in the last part, we're going to look at some memory isolation failures, how the ability for DRAM and SRAM to isolate different security domains from each other is really in a sorry state right now with Rowhammer and aging attacks and a variety of other things. So I think it would be really interesting to see how isolation is not really working that well. And as I present each of these attacks, I'll give you the source information, where to go learn more information about these attacks. And then also I'll share with you some ideas on how we can address these attacks as hardware security professionals. So let's get started. So the first one is actually an attack I worked on with students from my EECS 573 Microarchitecture class here at University of Michigan. And this was a really fun project. Basically, we were trying to demonstrate that Rust, which is a programming language, is a relatively new programming language that claims to have complete memory safety. And by that, the developers of Rust claim that it's not possible to overwrite past the end of a buffer array. It's not possible to overread past the end of a buffer array. It's not possible to use a dynamically allocated buffer after it's been freed. And I think this is generally true until you start to consider the possibility that the underlying microarchitecture may be violating some of these claims. So in this particular project, and we made the code available, a bunch of people have run it online, so you see the GitHub link down below. Go and try it yourself if you like. We implemented Spectre v1 attack in Rust code. So basically what happens is this gadget function right here, which has it's got to check to see if you go past the end of the array, but you don't necessarily need that in this code. We do that just so that when we give it the incorrect indexes, the code doesn't fail. Because if we didn't have this this check here, then what happens is that Rust inserts its own checks in the actual indexes to the array. So what's happening with Spectre here is we're training this branch to think that it is a legal array location, and we're training this internal branch that's added by the Rust compiler to also think this is a legal address. And then we give it an invalid address that goes past the end of the array, and then we use that to access a second array which is evicted from the cache. It's just standard Spectre attack. That's it. The second array is evicted from the cache, and then the value we read loads in a single cache line. And then we can look to see which one of those cache lines in array 2 was brought into the cache, and that'll tell us what val is, which is a value that's past the end of the array because we trained the branches to go past the end of the array. And this works on safe Rust gadget code. This is the gadget it works on. Now, what is safe Rust? Safe Rust is Rust that doesn't have any loopholes in it to try and get past the bounds checks on memory accesses. So this is a arbitrary buffer overread on Rust, on safe Rust code. And we demonstrated this on Intel. We shared this on online, on our social medias. And we also had a number of people tell us that it works on AMD as well. And it works using the latest version of the Rust compiler. Now, why is this important? A couple of reasons. One is, we see a lot of movement in the Linux community to allow Rust code to be integrated into the kernel. One reason why this is interesting is it would be possible to make tightly integrated Rust drivers and then use the memory safety of Rust to prevent that driver from poking around and looking at other parts of the kernel. But if there are arbitrary buffer overreads implemented by the microarchitecture, then we can't make those guarantees. And then really the key point here is that Rust claims to have memory safety, but we're demonstrating that you can read past the end of arrays, do arbitrary overreads. So, is Rust really have memory safety? So we disclosed this to the Rust developers, and they told us that it's not their problem. This is really, they said it's an Intel problem. And, and I guess Intel architecture is causing this problem, but, somebody probably should fix it, or Rust should not claim to have complete memory safety. And which really begs the question, who's responsible for fixing this? And everybody's kind of pointing at everybody else. I will say that it's the most expensive to fix in the microarchitecture. It's the cheapest to fix if the programmer does it. It's slightly less expensive if the compiler does it. I mean, both of those would be at the Rust level. The OS or the microarchitecture, if they fix it, it tends to be very expensive. So that's a really interesting question. I don't know the answer to that question, but it is interesting to consider who's responsible for fixing this. In the very least, Rust probably wants to should probably put some, caveats on their complete memory safety, because it is not complete. The second attack, another Spectre attack, it's called the iLeakage attack. And what's really interesting about this attack is if you've studied Spectre in the past, if you look at my earlier episodes of this series, you'll see that the way Spectre works is you train branches to access memory they can't normally access, and then you use that memory value to index into a second array. And then you use cache side channels where you're probing the cache to see which one of those entries in that second array was loaded. The index of that loaded value will indicate, what the value was that you were trying to read. And so this requires that you have the ability to time whether or not a memory access to array 2 is a hit or a miss. This is a high resolution timer, because out of the L1 cache, a hit or miss is a difference between a few picoseconds versus a few nanoseconds. So you need a really high resolution timer. So one of the defenses that was instituted in browsers to stop Spectre meltdown in JavaScript was to eliminate the high resolution timers. So for example, Safari, Firefox, Tor browsers all have low res timers on the order of a few microseconds to even milliseconds. And so it becomes very difficult to measure those low latencies. So what this work does in iLeakage is it uses race conditions to measure whether or not an access was a hit or a miss. It's a pretty simple idea, very clever. And the basic idea is we're going to write a 0 to a variable shared between two threads. Okay, so initially we write a 0 to it, and then we send off the two threads. One thread is the reference thread, and it's a thread that takes longer to execute than a cache hit in the other thread, right? So this is a data-dependent instruction chain, and at the end of this data-dependent instruction chain, we're going to write a 1 to the shared variable. The probing thread right here is simply going to access the memory that we want to know if it's a hit or a miss, and then it's going to read the value that's in this location. Now, if this is a hit, because this data-dependent chain is, let's do the hit example. If it's a hit, this data-dependent chain is going to be longer than it takes to get to this read, so we won't see this write. There's no synchronization here between these two threads. That's called a data race. So we'll see a 0 value come back from the memory system. In the event we get a miss, this is the miss case, where we get a long miss, this data-dependent chain will finish first, we'll write a 1, and then after the miss, we'll read this and we'll see a 1 from that shared variable. So if you see a 0, it's a hit. If you see a 1, it was a miss. And it's fine-grained resolution timing. Really fantastic piece of work, really clever, and you don't need any timers to do hit and miss detection. And I think really the key takeaway here, and just put this one in the bank. I don't think you'll ever be able to, you'll never find a counterexample to this, is you cannot stop your attacker from measuring time at any resolution, right? If your defense is don't let the attacker measure time, then your defense is by definition very, very weak. And this is because we all live in the same time and we can measure time. There's two options when a time is very small and we don't have high resolution counters. One is to do really cool stuff like this, to build events and then order those events and see which one happened first. The second thing you can do is you can just do your hit detection millions of times and let the time differential accrue between the hit and the miss case until you can measure it with a low resolution counter. So it's just really the case that never should your defense be, I'm not going to let my attacker measure time. All right, next attack. It's called Pacman. This attack breaks a really interesting and novel security defense that is covered in the earlier part of this tutorial series called ARM-PAC. PAC stands for Pointer Authentication Code. What an ARM-PAC is it's a 16-bit hash code that's tucked into the upper part of virtual addresses. On an ARM machine, you've got a 64-bit virtual address, but the virtual address space is only 48 bits. So there's an extra 16 bits that are they're not used. So with ARM-PAC extensions, that upper 16 bits becomes a hash of the pointer value. And that hash is a keyed hash, like an HMAC, so that to create the PAC, you need to know both the value of the pointer and the secret context or key that is stored in the microarchitecture that's not visible to software. And what makes this defense so fantastic is it prevents someone from taking a pointer from outside the system and injecting it into the system, which you have to do for a buffer overflow, which you have to do for return-oriented programming, which you have to do for virtually every single attack from the software side. So by preventing forgery of pointers, we provide a lot of resistance against a wide spectrum of attacks. So, A+ for this particular defense. The problem is with 16 bits, you can probably every once in a while guess, but you're going to get a lot of exceptions until you guess that, right? There's only, there's only 2 to the 16 possible PAC cases, and then if you guess the right one, you have a valid pointer that you can fabricate. So what Pacman does is it's searching for a way to check and see if a PAC code is correct in a silent fashion. And the way it does this is in Spectre misspeculation. So the basic attack is we forge a pointer, we put a random PAC on it, and then we use misspeculation, Spectre misspeculation, to we allow it to authenticate that pointer in misspeculation, and then we do a load with that pointer in misspeculation. Now, if the pointer's invalid, this pointer authentication will essentially zero out the pointer, and so the load will bring nothing into the cache. If we evict from the cache the target of the forged pointer, then what we can do is we can just keep guessing packs until we get an authentication which in misspeculation is correct, and then it loads the correct value into the cache, and then it squashes but leaves the value in the cache. Then we probe the cache. If the value was in the cache, that is a correct pack. If the value is not in the cache, it's not a correct pack. Do that 2 to 16 times, and you will always be able to forge a pointer. Super clever attack. They're really taking advantage of misspeculation as a way to do silent failures. How do you stop this attack? It's really tough, right? I mean, one way to stop it is don't allow speculation on loads, right? Which is like, nobody wants that. That's going to slow down your machine plenty. So it's really unfortunate that this happened. You need more entropy in your pack in order for this to really be stopped. But that said, I wouldn't say ARM pack is not useful. Doing this attack is very hard. So having ARM pack on a machine certainly makes it harder to attack, even with the existence of this bypass mechanism. So that's some novel Spectre attacks. I love Spectre for many reasons. In particular, it really hypercharged hardware security. I'm really thankful for that. But it's just the gift. It's just truly the gift that keeps on giving. Lots of solutions in the hardware vulnerability space can be centered around these Spectre-like misspeculation execution attacks. Now I want to move on to novel side channels. When you think of side channels, typically, most people, the first thing they think about is program behavior side channels, control and memory accesses. But when you think about microarchitecture side channels, you always think about the branch predictor and the caches. And there's loads, jump over ASLR, prime and probe. There's loads of stuff that I even covered earlier in this tutorial surrounding those two things. So now I want to look at some other side channels. And sort of the subtext of this section that I want you to keep in mind is there are side channels everywhere. And if you think you can get rid of all the side channels, you're probably wrong. There's probably some you don't know about. There's some I don't know about. There's some nobody knows about. So it's just such a rich array of side channels in the microarchitecture. And so, the corollary to that is, if you want to stop microarchitecture side channels, plugging all those leaky holes is probably not the right approach. Maybe you want to encrypt stuff. This is what I always advocate. But it's something to keep in mind when you're building a secure machine. So let's take a look at these attacks. The first one is called GoFetch. And it is one of the early versions of Prefetcher side channels. And Prefetcher side channels is going to be a rich area of research in the next few years. The Prefetcher is doing, on many machines, is introducing semantics that programmers did not specify, and those semantics can leak sensitive information. That is a pure microarchitectural side channel. So in this particular attack, GoFetch, the Apple M1, M2, M3 cores, which are in Apple desktop products, they have what's called a DMP prefetcher. Data-dependent miss prefetcher. And the prefetcher, what it does is when it sees a miss, it brings in the block of storage from memory, and then it scans the data in the memory block to see if any of those are pointers that are within a 2 gigabyte window of where this block was in the virtual address space. So they're saying, they're asking the question, are there things here that look like pointers that point to roughly the same location in memory that this pointer that I used to fetch this block is pointing to? Okay. So A, that's a pretty good idea, because if it's a linked data structure like a tree, you're going to start fetching the nodes of the tree. That's great for performance. From a side channel standpoint, it's kind of a deadly sin, because you're using data of the program to affect the behavior of the microarchitecture. That is what every side channel lover is looking for. So it is a wickedly bad, in my opinion, side channel. And to demonstrate this, the attackers, they apply it to what's called data oblivious ciphers. Data oblivious cipher code is code that's written such that the behavior of the code is not dependent on the data that it is processing. That is the way that we get rid of program level side channels. That is the side channels due to branches and the side channels due to memory access patterns. When you write a data oblivious code, the programmer's expectation is, I've eliminated all data dependent behaviors from my code. Therefore, as you run my code, you'll never learn anything about my data. These have become very popular in the post-quantum NIST cipher competition, because they're required to have these implementations. And they should have those implementations. That eliminates a lot of attacks that we've seen in the past. The problem here is that DMP Prefetcher is scanning the blocks that it's printing in, and it's doing prefetches based on values that are in the memory blocks. And it's violating the principles of data oblivious code behavior. It's adding behaviors to the program. So what they do is they basically look at these post-quantum ciphers. Psych is the specific one they look at. And they specifically look for situations where they can manipulate the ciphertext so that under certain scenarios of a 0 or 1 bit key, they create what looks like to DMP a pointer versus what doesn't look like DMP to a pointer. And when it looks like a pointer to DMP, DMP starts to make some prefetches. Those prefetches contend with the normal memory accesses that are being done by the data oblivious program. And so now all of a sudden the data of the program is slowing itself down. And you can see in this graph where when the secret bit they were trying to identify was a 1, the program was a little bit slower on average. And when the secret bit was a 0, the program was a little bit faster on average. So despite being data oblivious code, they are revealing secrets, and it's because of the microarchitecture. So that is really the responsibility of the microarchitecture. The programmers had nothing to do with this. How do you stop this? Well, you need to disable data-dependent prefetching. There's nothing the programmer can do other than say, oh, please, hardware, turn off this thing that is really wrecking my ability to build data oblivious code. I think another interesting way to stop this would be to explore the possibility of data oblivious executions in the microarchitecture. I think, Intel started to do this with the DISA instruction set extensions for fixed time execution. So, really fantastic side channel, pure microarchitectural side channel. Totally breaks data oblivious cipher codes. And hard to fix without just turning off the prefetcher. Now, the next one, I again, I love all these attacks. But this one I really like because Rowhammer isn't very useful, in my opinion, until I read this paper. Rowhammer is an integrity attack. And an integrity attack what it means is we're going to flip a bunch of bits. And when you're flipping bits, you generally don't know which bits. There's a bit of a pattern to it, but you don't know specifically which bits are gonna flip. So really, it's just kind of a way to troll other VMs and basically just wreak havoc on a system. In a sense, it's almost like a denial of service capability. To me, that didn't seem that interesting. I want to figure out how can I use it to steal information or manipulate the execution of this program. I think these are more interesting attacks. So while Rowhammer is very important, I never really saw what the killer app for Rowhammer was. And when I read this paper, I thought, okay, now we got some interesting stuff Rowhammer can do. First, let's just talk briefly about what Rowhammer is. Covered it earlier in this tutorial series, but Rowhammer is basically where if you want to flip bits in a DRAM row, you just access the rows that are above it and below it physically in the DRAM, and that will speed the discharge of those bits and cause bits to flip. Now, what they recognized in the Centauri Rowhammer tracking attack is that when you Rowhammer memory, the pattern of the Rowhammer, while it does change a little bit based on voltage and temperature and other stuff like this, it's mostly static. And by using fuzzy signature mechanisms, you can actually generate a signature. So here we got memory module A and memory module B, and you can see that over time, this is one time we took a signature and another time we took a signature. Just looking at its Rowhammer bits, they're pretty similar. And if you have a sort of a fuzzy signature mechanism, you can very quickly identify which one of those. If I show you a third set of signatures, you're going to be able to tell me instantly which one is memory module A, which one's memory module B. And so what they're doing is that, in JavaScript, you could do this hammering, and you could essentially track a DRAM sitting in a system without permissions to track that system. And what's interesting about this particular attack is in the industry right now, there's really a movement away from tracking. If you look at things like Google Topics is an effort to, instead of track users individually, to track 16 of their interests, and not allow the tracking of them specifically. I think that's very interesting. Of course, advertisers want to track. They want to know exactly who you are and where you go, and things like topics do not allow that to happen. It only provides interest information. And so things like this could become a nefarious approach to doing tracking. There's a bit of a challenge here. You got to be able to do it in JavaScript. They talk about the fact that you don't always get to hammer the same memory, so they need to generate a number of signatures, and then eventually a system gets recognized pretty easily because they'll be able to hammer a piece of memory over again the next time they visit a website, for example. There's no permission needed. There's no evidence that it occurred. And they look at both the accuracy overall. What's the, when a bunch of machines come to a website, they get an accuracy of 96.97%. And the recall, this is the accuracy of a specific machine coming to the website repeatedly. For a specific machine, 90% of the time they identify that machine, that specific machine. So I find this really interesting. I find this means Rowhammer it's not just an integrity problem, it's also could potentially be a privacy issue as well. So definitely a topic to watch in the Rowhammer arena. Another side channel, cryptanalysis of trusted execution environments ciphertext. Trusted execution environments are basically ways to take all the data that's running in a process, and when it spills out of the core chip, out of the caches into the DRAM, encrypt all that data. Intel SGX does this, Intel TDX does this, AMD SEV does this, and this attacks on AMD SEV. Now, what AMD SEV does is it's encrypting the whole VM, and the goal of AMD SEV is to provide isolation between VMs. This VM should not be able to see the memory in the VM that's running next to it, even though we're sharing the same core and we're sharing the same DRAM. And that's because VM1 is encrypted under one key, VM2 is encrypted under another key. So even if you could see my DRAM, it's encrypted. So the way it does this is when information spills out of the core into the DRAM, it's encrypted with AES 128 using a per VM key that's kept on the CPU chip. And it uses what's called an XEX tweaked cipher. That means we take the information that we're going to send to DRAM, we XOR some address information, physical address information onto it. We encrypt it and then XOR information onto it again. That's by tweaking. What that means is that if I store like a 0 block to one location and then store a 0 block to the other location, in an untweaked cipher, all of a sudden you can see where all the 0 blocks are because they're all the same ciphertext. They're just encrypting zeros. And so by tweaking, they're all different because each one's at a different address. And so that XORing of the address onto the information that you encrypted makes a different ciphertext output. You only have to change one bit on the input and you'll get a whole different ciphertext output. In this case, we're changing 64 bits on the input for the physical, or on the order of 48 bits actually. And so it decorrelates this RAM, but it's tweaked. In the world of cryptography, we talk about tweaked ciphers and semantically secure ciphers. Tweaked ciphers are, if I look at these two addresses, I can't correlate them. But if I store the same information to the same address again, I see that I stored that previously to this address. Why? Because it's the same physical address. It's the same tweak. So I can see in a particular block of memory when information gets reused and appears there again because the tweak is fixed. Semantically secure is a little different. That's where you actually inject randomness into the cipher and you store the randomness and metadata in some protected place. In this case, it's just all random. Just, you can look at, if I store 0 to 1 location over and over again, it's just always different. But that's not the case for this particular machine. For this particular machine, if you see the same location, if you see the same ciphertext in the same location twice, that means that what was stored there previously is stored there again. And they use this property of tweaked ciphers to attack the virtual memory kernel. So specifically what they're doing here is they're, one VM is making calls to OpenSSL on another VM, and it's doing RSA functions. Inside RSA is a function called bn get 5 bits. We get bits 5. This gets 5 bits of the secret code, which then feeds into these, fixed exponential window, fixed times exponentiation algorithms, which typically take 4 or 5 bits. Now, what they're doing in this attack is they're repeatedly forcing the VM to go to sleep. And when it goes to sleep, it writes out an encrypted register block to memory. And then the attacking, in the threat model, the attacking VM can look at that encrypted memory. In that encrypted memory is both a return value, RAX encrypted, and a return address, RIP, if RIP is the return from bn get 5 bits. So if we get that VM to sleep just when returning from bn get 5 bits, which I can tell by looking at the return address, okay, it's encrypted, but it's going to be the same value every time it returns. So once I can identify what that encrypted value is, then I'm golden. If I see that return IP, then I know RAX is 5 bits of the RSA key. Now, there's only 32 possible things that get stored to that RAX. Why? Because, okay, it's a 64-bit value, but the function is only returning 32 different things, 5 bits of the private key. So now I just have the goal of figuring out, like, across all this key, what are the 32 different symbols and what do they mean? And they have a number of clever ways to try and figure out that information. So cool. Such a great attack. And then very quickly, they're pulling RSA keys out of another VM. Why? Because tweaking doesn't stop correlations at a single location. So how do you stop this attack? Well, the way AMD stopped this attack is before they encrypt this block, they just basically XOR a random value all the way down the block. Okay, it's like a chained XOR all the way down the block. So now, I fed some randomness, what we call salt in the world of cryptography, into this block. The attack's no longer possible. But that's just for the VM save area. The whole rest of the VM is still tweaked and probably not salted. So AMD also released a document to tell programmers how to basically salt their own data. It turns out that the block size for AMD SEV is 2 64-bit aligned values. And that feeds into the AS128 engine. So if you have a 64-bit value that you want to protect, you have to align it, and you got to put 64 bits of randomness next to it. Otherwise, somebody could start to analyze what that value is. So not really fixed for this particular attack, but there's a lot of correlations that can still be exploited in these enclaves. In the original SGX, they actually used counter mode encryption, so you couldn't really do this attack there. But they got rid of that in Intel TDX. The VM enclave is what I've read, and so it's probably possible in that case as well. And now I should present my absolute favorite side channel. And this one I love because A, it's simple, and B, it's very surprising. It's in the power gating structure of the AVX2 unit. AVX2 is the 512-bit vector unit on high-end Xeon. Okay, and how many servers are doing 512-bit vectors? Probably not a lot. And so to save power, to make this a green design, if you haven't done a 512-bit vector operation for more than 1 millisecond, they power down the upper 128 bits. They basically have like a switch mechanism that turns off the power to that part of the circuit. And the reason why that saves energy is because you don't have what's called leakage through the circuit during that time. But if someone then comes and does a 512-bit op, you have to power up that grid, and that takes probably thousands of cycles to power up that grid. And you can see here that when the grid is powered up, I can do a 512-bit vector op in like just around 200 cycles, and when it's not powered up, it takes almost 600 cycles. So not quite 1,000 cycles, but hundreds and hundreds of extra cycles to power up that grid. And that is a loud side channel, loud. And it was used by the Net Spectre attack to try and do Spectre attacks over the internet. And there's a reference to that paper. Basically, the way you use this in a Spectre attack is when you want to communicate out a 1 or a 0, you don't do any AVX 512 operations, and then you make a call to your Spectre gadget. And if you want to send out a 1 bit, you execute an AVX2 instruction, which takes that 600 cycle delay, and then comes back. And then if you don't want to, if you want to send out a 0, you wait 1 millisecond till it powers down the upper 512, and then you send it into the gadget, and then you have the gadget not execute a big AVX2 operation. And so then it comes back right away. So you see this sort of this 500, 400, 500 cycle delay between those two operations. And then I asked the question, should this be mitigated? Should this be mitigated? And that's a really great question. Because, I mean, to mitigate it, you basically have to stop power gating. Because you can't just turn on stuff. You can't turn on stuff instantly. Because to turn it on instantly means you have to have the power grid up. And if the power grid's up, then you're leaking, then you're losing your energy. Right? And so, I don't think you should stop something like this. I think this you just have to tolerate. And you have to build systems that can tolerate the existence of these kinds of side channels. But people may disagree and want to turn on all their power all the time. Here's another power-related side channel. And this is called the Hertzbleed attack. Another super clever physical attack. It leverages what are called physical side channels. Physical side channels are side channels that leak information through power, temperature, sound, any kind of physical phenomena associated with computation. And to defend against physical side channels, you have to blind computation, or you have to stop the installation of sensors on your trust zone. Which begs the question, what if your microarchitecture is a sensor? And that's really the invention of Hertzbleed, is the recognition that a modern microarchitecture is a sensor for power. Now, how is a modern microarchitecture a sensor for power? Well, the way architectures are built today, you can't run a CPU at maximum rate all the time. It'll generate too much heat and it'll burn up the chip. And so what happens is you can run it very quickly for a short amount of time, or you can run it very quickly until what's called the thermal throttling mechanism slows down the system. And it slows down the system because when you slow down the clock, you consume energy at a slower rate, which generates less power and then controls temperature. Typically, it's called the thermal throttle, and it just prevents the chip from overheating itself. This can be due to the fact that you have a lot of computation, but you can even take the chip and put it in an oven and it'll start to slow down. It doesn't matter if the heat's coming from the outside or the inside. If it's too hot, you can't run that chip. You can't generate any more heat or you're going to burn up your transistors. And chips today can burn up their transistors. So these mechanisms are absolutely critical to solve what's called the dark silicon problem. So Intel CPUs, and basically every high-end CPU, have these thermal throttles. So what they do in the Hertzbleed attack, again, to get, attacking the psych algorithm, but they figured out in the psych algorithm that if they condition the inputs in a certain way, they could create what they called a computation chain. And that computation chain occurred when a ciphertext bit matched a key bit in a particular scenario. And when that chain of computation occurred, it would consume more energy. Now, it's data oblivious code. There's no change in how the code is running in terms of its control or memory access, but the computation has, more carries, more underlying circuit switching to compute the final result. So they condition it, they run these experiments, they run them repeatedly, and they see that when the bits match between the key and the ciphertext, it consumes ever so slightly more energy. And when it consumes ever so slightly more energy, as we allow that to continue, eventually thermal throttling kicks in, and now when these two key bits, the ciphertext and the key bit matches, then the algorithm runs slower because it's generating more heat, because this chain computation is doing more transistor switching. It's not changing the timing. What's changing the timing is the thermal throttling is saying, whoa, we got to slow down this clock a little bit because we're generating too much heat. Really clever, really clever. Hard to defend against, right? Hard to defend against. This to me, this is like a red flag in my mind. Because if you want to build trust zones, you have to disable thermal throttling, which means always slow execution, right? Because go read about, dark silicon. We can run faster than we can remove heat, but only for a certain amount of time. If you disable thermal throttling, then you're always running slow. We have to separate microarchitecture sensors from the trust zone. That's hard because if we're on the same chip, the heat will travel through the materials. And so the heat from the main core will travel into the trust zone, and the trust zone heat will travel into the main core. So hard to build a thermal barrier there. And, really the only alternative is really use what's called blinding, where you decorrelate what the computation is from the inputs of the computation. It's called blinding. And that's great, and that's a super solution, but it's not always possible. So hopefully your algorithm supports it. If it doesn't, this is a very, very important side channel. It's using the microarchitecture to sense and implement analog physical side channels. Really fantastic work. And then I wanted to present PortSmash, which I think what's great about PortSmash is it really opens up your mind, fifth eye, to what are the possibilities of side channels. And normally we think of state like branch predictors, microarchitecture state that's shared as a side channel, but really it's just all about contention. And you don't need state for contention. You can contend on a bus. You can contend on a port to a functional unit. And what PortSmash does is it contends on ports. So the channel that is being formed is in the contention between a SMT, secure multi-threading thread 1, and secure multi-threading thread 0. So two different threads trying to access the same, let's say, a multiplier on port 1 in this Intel architecture. And as they contend, it adds delay to the loser, right? Because you can't do two multiplies at the same time. One thread goes first, the other waits, and then goes. That increases the delay on the other thread. So in the PortSmash attack, They're again trying to steal keys out of an OpenSSL signature generation. They're specifically looking at implementing contentions on port 1 in the Intel microarchitecture, which is where the multiplier, the integer multiplier, sits. They're running this OpenSSL signature generation, which has got loads and loads of integer multiplies in it. And then off to the side, a second hyperthread is running CRC32 instructions, 144 back-to-back dependent instructions. Those also use port 2 because the bit scan capability, port 1. The bit scan capability is also on port 1. So you've got two threads contending for the multiplier port. One is using it for multiplies, the signature generation in OpenSSL. The other is using it for CRC32 bit manipulation instructions. And so the SPY thread is just running 144 back-to-back bit manipulations. And then it's timing how long it takes to do each one of those. And then the more there is dilation in that time, the more multiplies are happening in the signature generation in OpenSSL in the other thread. And so then you end up getting this sort of sequence of degrees of multiplies in the contention by how long you're dilating your own latency. And then that forms a signature. And then the goal of PortSmash is then to go look at, they analyze the signatures from two specific functions, an add function and a double function, which was implemented for the signature generation. And they can see what the multiply contention looks like for the add function. And you can see what the multiply contention looks like for the double function. And then they can see that it double, add, double, add. And then by knowing that sequence of calls, due to this contention on that port 0, they can infer key bits. Not all of them. They got to do a little bit of recovery of key bits. But oh my gosh, in 4 hours, they're pulling secret keys out of the other thread. Such an interesting attack. And it's really because of this close, tight sharing that SMT provides, and the fact that you don't have to share state to create a channel. You just have to contend for a resource. How do you stop this? Well, turn off SMT. That's really expensive, right? Because as microarchitects, we know how little utilization we have of the underlying microarchitecture. So we want hyper-threading. We want to be able to tolerate, L1 cache mislatencies. And you don't get to do that unless you have SMT. So that's expensive from a performance standpoint. The better way to do this is to write a data oblivious kernel. If you write a data oblivious kernel, the sequences to the multiply is fixed for every input. It's harder to write that code, but if you can write that code, and you should write that code, then if someone's contending with you, they'll see the same signatures every single time. And they'll learn nothing. Why? Because the way you use the multiplier reveals nothing about the code. So that's the key to stopping this particular attack. But so interesting that you don't need state to create these channels. So interesting. And then finally, I want to just spend some time talking about memory isolation failures, where we put different security domains into memory, and they shouldn't interact with each other, but there's lots of examples where they do. The classic inter-domain interactions in DRAM, of course, is Rowhammer, where if you have a row in the DRAM and you repeatedly access the rows around it within a single refresh cycle, you can speed the discharge of that center row, leading to bit flips. And so with each generation of DRAM, DDR2 to DDR3 to DDR4, they've been trying to stop Rowhammer. They didn't do it in 3, they didn't do it in 4. And for a while, 5 looks like they'd finally stopped it. And then, a few months ago, DDR5 got Rowhammer. And basically, it was pretty straightforward how they did it. They just basically analyzed different instructions to see how many activations could they get within a single refresh window. They got up to 300,000 activations, which in today's Rowhammer world, that's a ton of activations. There's some attacks that only need like 5,000. So that's a generous number of activations. That means how many times can you hit a particular line in the DRAM past the caches within a single 32 millisecond refresh window. So fairly straightforward to implement it on these. And they found for different machines, Intel and AMD, and for Samsung, Hynix, and Micron memories, they were able to Rowhammer pretty much everything on every machine, except Hynix is a little tougher on AMD. And there was actually one Hynix DRAM that they couldn't Rowhammer on Coffee Lake either. So, but pretty much everybody except this one Micron memory here was Rowhammerable. So, is it stoppable in the DRAM? It's yet to be seen. But you know, it seems like if they're using targeted row refresh, where you look for how many accesses to a row and then you refresh it selectively, that doesn't seem to be working. I'll just say, if you care in today's world, if you really care about what's in your DRAM, just encrypt it. Because if somebody, corrupts it, when you decrypt it, it'll be further corrupted. But you could also use a form of encryption called authenticated encryption, and then when you decrypt it, it'll actually say, "Oh, I'm sorry, this value was corrupted in memory." It'll actually tell you when someone Rowhammered your DRAM. So check that out. And then another form of isolation between memory processes is address space layout randomization, ASLR. The idea behind ASLR is every time I start a program, I'll randomly place where its stack, code, heap, and global data is in the address space, so that when one process wants to attack another process, or when someone from the outside world wants to inject information, pointers and such into my program, they don't know what the addresses are that they want to inject into the program. And so this forces the attacker to do what's called de-randomization, to discover the location of objects in a remote process on a machine or even remotely over the internet. And this was hard on a 32-bit machine, incredibly hard on a 64-bit machine. And the ANSI attack really, if you're attacking from one process to another on the same machine and sharing caches, essentially defeats 64-bit ASLR. The basic idea is that we're going to evict the page tables from the cache. We can do that by just overwriting the cache with our own data. We're going to evict the TLBs, and then we're going to make a request to an object in another address space. That's going to miss in the TLB, and it's going to walk the page tables, and the page tables are going to be brought into the cache. And what ANSI does, the ANSI attack does, is it tries to analyze what was brought into the cache on this page miss, and it starts to build a picture of what part of the address space in the multi-level page table was walked by looking at what was brought into the cache. What of my data was displaced? And they're very clever. They can infer basically all the information and fully de-randomize the thing you're touching in the other address space. And once you know the address of one thing, you can know the relative address to everything else. Such a amazing, clever attack. It takes, multiple calls to get this information, but over time, as you go lower and lower here, we have fewer bits of entropy on where these addresses might be. And then very quickly you get to within guessing distance. We only have to guess a few bits, or you can know exactly where this thing is in the address space. How do you stop this? Well, probably the easiest way to stop it is to use a randomized hash table to do your PTE lookup. That's great on RISC-V because software defines the hash table. Can't do that on x86 because the hash table, the multi-level page table is defined in the architecture. So you're stuck walking tables that could be brought into the cache. Then another possibility is to partition the caches and to reserve part of the cache hierarchy to, or flush the caches whenever you get a page fault. But that can be very expensive, both of those things. So not a lot of good attack solutions here. And basically on x86, if you're willing to invest in this kind of attack, you can de-randomize anything. Oh, more fun from Rowhammer. This time, Rowhammer to read storage. This is such a clever attack. Normally, when you think of Rowhammer, you think integrity attack. It's going to break address space information by allowing me to flip bits in another process. In this particular case, I'm going to use Rowhammer to read information from another process. Really clever attack. The basic idea is as follows. I'm going to hammer 2 rows from the other process, and I'm going to use it to hammer a bit in my process. Now, how do I get to hammer another process's rows? Well, I just have to, they have this thing called frame feng shui, where they can cleverly use page caching and allocating and deallocating storage to get a row of the DRAM to be partly my memory and partly the victim's memory. And then I hammer my memory here, which essentially hammers the row that the victim is in. And then they recognize that when my bit is a 1, so my bit's always a 1, when the other address space, when it has a 1 bit, and I'm gonna basically map the same address above and below. They talk about how to do this. They can do it if it's not possible, but they have lots of tricks. If the bit I want to read above and below me is a 1, what happens in Rowhammer is when I got 2 1s next to me, I can hang on to my storage longer for some reason. I'm not sure what the effect is, but it has been recognized in a number of papers. When the bits on both sides of me are 0, then it's more likely to flip my bit. So essentially, I don't know what these 2 bits are. This is my bit. I set a 1 here. I hammer our shared rows here. And if my bit flips, then I know that the bit in the other address space was 0. Oh, so cool. If it doesn't flip, then I know the other bit in the address space was a 1. Modulo the fact that this is row hammering, so things are always a little bit fuzzy. So they're pulling, RSA keys out of the other address space, and then they're using heuristics and brute force to finish to correct the bits that they didn't read correctly, and they're able to pull keys out of another address space. So interesting. Now, Rowhammer is not just a integrity problem; it's also a confidentiality problem as well. So interesting. Again, if you care about your data in DRAM, encrypt it. And then this attack is a transistor aging attack. And it recognizes that when transistors switch, they age. Right? It's like your heart. Every time your heart beats, you're closer to the time when it's not going to beat anymore. Just the same thing for a transistor. Transistor has these little failure modes like BTI and hot carrier injection, HCI, where over time, the transistors, as you use them, get progressively slower. And they recognize in this paper that this happens not only in like logic, but also happens in SRAM. And so what happens is you can put a value in SRAM, and over time, it'll sort of bend the what are called the cross-coupled NAND gates in a way where when you power on the SRAM, it'll naturally come to the value that's been sitting in it for a long time. It has to do with the metastable races that occur when you power on an SRAM, and because a value is sitting there, it kind of bends one side to be a little stronger than the other, and so it easily comes back to its original value. It's like the old CRT monitors when you'd had a single image on it for a long time. It would burn the image into them. We're essentially burning with wear out values into SRAM. And so they use this to steal keys. Basically what they do is they put key information into a little IoT microcontroller, and they let it sit there for a long time. Now they accelerate the aging. The way they accelerate aging is they add heat and voltage to the system. When you add heat and voltage, all the aging mechanisms accelerate, but this would probably work if you had years to do this experiment as well without heat and voltage. And so after they've aged these cells with these AES keys in them for a while, then what they do is they reboot the system, but they do it in a way where memory is not clear, so that the value of memory is its power on value. So all the little races and all the LLS RAMs just sort of resolved. And when you get up into the system, you can see they do this by taking advantage of a debug mode. And they get 97% accuracy. Those initial values coming out of those bits where the AES key was sitting for so long are exactly the AES kit modulo 3 bits changed. So clever. And true loss of isolation here. So how do you stop this attack? You gotta clear memory at power up. You gotta clear memory at power up. Don't prevent overtemp or overvolt operation. That's important. And then if you're a programmer and you're wary of this, you can always blind your key values by like mixing in some random salt and then remixing in random salt on a regular basis. Just store the salt next to the key and then store the key XORed with that salt. Now, essentially, there'll be no bias on that value because the randomness will eliminate any bias. And then finally, FUX.net, I'll call it here, is a attack that essentially destroys IoT devices by wearing out their flash. And this is an IoT specific attack. Very interesting. First, just a little background. What is NAND flash? NAND flash is the typical flash you see in the IoT space, and it's storage that can hold its value when the system is powered off. And the way it does that is by doing what's called generating trapped ions in the floating gate. That same aging mechanism that I talked about earlier in this presentation, they're leveraging here to store information. So they sort of pre-age this transistor by forcing ions into these insulators, and they just stay there when the thing is powered off. Then to get rid of them, you have to reverse the voltage and push them out. And what happens is this is very damaging to the cells. And so your typical NAND flash cell can only be written 100,000 times, and then it doesn't work anymore. It's literally broken, and it doesn't store values. It's just stuck on whatever value it was biased to. And so, okay, in your SSD, it's not a big deal because you got a terabyte there, and and does wear leveling, so you'd have to write a terabyte 100,000 times, and that's going to take years to do that. But in an IoT device where you've got 256 bits of flash to store your configuration information and a little bit of statistics, you can overwrite that 100,000 times in a few minutes. And that's what this FUXNet attack did. Is it basically got its way into IoT routers, IoT gateways. So these are like gateways that would control little IoT devices. And they installed some software that just overwrote the flash. And they did it until what they read from flash was no longer what they wrote. And then they moved on to the next block, and they continued until there wasn't enough flash left to hold just their little tiny program, and then they stopped. And these devices are bricked. They are no longer useful. They cannot be fixed with flashing. They burned out the flash, and they have to replace the devices. This is a physical destruction attack. Really, really interesting attack. And really the way to stop this, you really need hardware to stop this. Because if you can get in there with software and there's no protections, there's no way to stop software from writing to flash, then malicious software will destroy that flash. So the way you stop is you have to have key or signed writes to the flash, and that signature, you can use PKI, which is expensive. Some TPMs do that. Or you can just have a private key that nobody knows about except the manufacturer, and then you destroy the key once you've written the flash. So the key's only evident in the software updates. Not as secure, but it's better than nothing at all. And then if somebody just comes onto the system, they can't write the flash because they don't know what the key is. But you're going to have hardware support. And this is a key vulnerability for IoT because there's so little flash in those devices. So easy to override it 100,000 times. Burn it out. All right, that's 2021 to 2024 attacks. Thanks for watching this video. If you got any questions or comments, please don't hesitate to reach out to me or leave a comment on this video. And take care. Thanks for watching. Be sure to like and subscribe.